Welcome. We will continue on our journey. We're going to start discussing the next chapter where we're going to be going over different reactions and different calculations. So let's begin. We're going to start simple on pretty much going over on how we represent a reaction. Notice that on your left side, you're going to write your reactants, and you kind of already know this. Those are going to be your ingredients. The arrow indicates that these reactants are going to go through a change. And then on the other side, on the right side, you're going to have your products. That's going to be your new whatever you created, whatever you synthesize. Now, sometimes we're not going to be able to see those changes. They're not going to be as obvious. Sometimes you're going to see sometimes you're going to have powder and then you're going to end up with gas, or sometimes there will be a color change. Sometimes it may not be a color change. What I'm trying to say is that in chemical reactions may take place without an obvious sign. You're not going to be an obvious change. So you have to be careful. You can't just say there was no reaction. You actually gotta have to look at the phases. Sometimes you're gonna have to know more of the physical properties and chemical properties before you said there was no change. It's not going to be obvious. The changes occurring at the atomic and molecular level determine whether the reaction took place or not. And then you're not going to be able to see the atomic or molecular changes, not always. Sometimes you will, but not always. Now, before we get into this chemical reaction, we're going to be able to go over certain rules, certain laws that we have to go over before starting to write reactions and analyzing and all that stuff. So the amount of every substance used and made in a chemical reaction is related to the amount of all the other substances in the reaction. Basically, we're going to be following two laws for these reactions to actually occur. It goes back into the whole matter cannot be destroyed, created, nor destroyed. So that's where we're going to start, that law of conservation of mass. And for us, for that law to be valid, we actually are going to have to balance the reactions. All of this falls under this umbrella called stoichiometry. So pretty much stoichiometry is we're going to be making a relationship between the reactants and the product. So we're going to be relating them. So at this point, I hope that you're very familiar with dimensional analysis because we're going to take it to the next level. So stoichiometry is pretty much a numerical relationship between your reactants and your products. We are going to balance equations. In order to balance them, we are going to be adding coefficients to the equation in general. That changes the amount of moles that we're going to have either in the reactants or the products. When we have a reaction such as the one that I'm indicating, there's different ways of reading it depending on what you're trying to accomplish. For example, the first, we can read it as when it comes to molecules, we can say we have 2 molecules of that reactant and it's going to react with 25 molecules of your oxygen. This will yield, or this will form 16 molecules of carbon dioxide and 18 molecules of water. That's one way of reading the equation. However, we can also read it when it comes to moles, which is the one that the terms that we're going to be using more often. We can say that we have 2 moles of octane reacting with 25 moles of oxygen, and this will yield, or this will form 16 moles of carbon dioxide and 18 moles of water. So the ratio will be 2 to 25 to 16 to 18. So, and we're going to be making that relationship, because what happens if you only start with 1 mole of this reactant, how many moles of water you're going to yield. It's going to be different, right? In this case, it's easier to see because you're just going to do half of it. But as you move on, you're going to see that things are a little bit more complicated. Now, so when we are going to, this is a combustion reaction. And the reason why it's a combustion reaction, and you're going to have to know that this is a combustion reaction, is because it's going to react with oxygen. And in a combustion reaction, your products are always going to be carbon dioxide and water. So in this reaction, we see how methane, which is an organic compound, a natural organic compound, is going to react with oxygen and is going to yield carbon dioxide in water. Notice a couple of things. In this reaction, it's not telling you the state. It's not telling you the phase, the state, like whether it's a gas, a solid, a liquid, or aqueous. And then oxygen is not telling you the state. So that's one thing that we have to look at. Also notice how many oxygens you have on your reactant versus how many oxygens you have in your product. So they are different, right? Here you have two oxygens, and in the product size you have 3 oxygens. So going back to the law of matter, we're actually not following it in this equation. So first thing you need to do is you need to indicate the state, whether it's a gas, a solid, or a liquid. For right now, you don't know unless I tell you the state. But in the future, you're actually going to predict the state. Now, if you look at it here, like I mentioned, you have 2 atoms of oxygen in your reactants, yet you have 3 atoms of oxygen in your products. So what we need to do is we need to balance the equation. If we balance, we are going to be following the law of conservation of mass, because we need to make sure that nothing is, no atoms disappear in the process of our reactions. We must account for all the atoms on both sides of the equation. Notice also we have 4 hydrogens on your reactant side and we only have 2 hydrogens on your product side. Once again, this does not follow the law of conservation of mass, which means we are going to have to balance the equations. And the way we're gonna do it is by balancing the number of each atom. We wanna make sure that they're the same on both sides. And we are going to do that by being able to add coefficients, which is the number that is gonna become right before the chemical equation. The 2 that was added in front of water applies to the hydrogen and applies to the oxygen. For example, here is indicating that 2 times 2, that means we have 4 hydrogens and we have 2 oxygen. That 2 applies to that oxygen. Now in total on the product side, it looks like now I have 4 oxygens because 2 plus 2 is 4. And on the reactants, I also have 4, which means that my oxygens are already balanced. Notice that we are never going to change the subscripts. We do not touch the subscripts. We only touch the coefficients. So now if you notice, the equation is actually balanced. We have the same number of carbons, we have the same number of hydrogens, and we have the same number of oxygens on both sides. So we are following all the laws, all the rules. Our equation is balanced. Sometimes people like to do what is called a T-chart, where you put the reactants on the left side and we put the products on the right side. Every time you change a coefficient you added, you need to double check everything, because for example here, notice that our intention was to put the coefficient to change hydrogen. However, by us doing that, we also change oxygen. So it's always important to double check your work at the end to make sure that you have the same number of atoms of each atom. Here we have an example. Notice in here it's indicating the phases. So it's a good equation. It's telling us the phases, and it's also telling us that this equation is balanced. You have 1 magnesium, you have these 2 chlorines, right? Because this 2 goes to the chlorines too. So you have 2 chlorines and you have 2 hydrogens. So this equation is already balanced. Here's an example equation. How will you balance this equation? One thing that I want to mention is that if you have an atom, such as lithium by itself, like it's not connected to anything else, I always advise it that you leave it until the end because it will make it easier. So if I was to do this, I will do a T-chart where I put my reactants and I put my products, and then I do lithium, I do hydrogen, and I do oxygen. Currently on my reactants, I have 1, and in my products, I have 1. For hydrogen, I have 2, and for my products, I have 3. For oxygens, I have 1, and for my oxygens, I have 1. So notice how the only atom that is not balanced is going to be my hydrogen. What I'm going to do is, since I have 2 hydrogens on my reactants, I'm going to add a 2 to my products. Now I have 2 hydrogens. Oops, sorry, that was wrong. Give me 1 second. Okay, let's do this again. So here's my T-chart with my reactants, my products, the lithium, hydrogen, and oxygen. So I have 1 hydrogens, I have 2 and 3 oxygens, I have 1 and 1. Okay, so it's my hydrogens that are not balanced. So what I'm gonna do is I have 1 lithium, 1 lithium. Now let's see, what I have is a 2 and a 3. So what I'm going to do is I'm going to add a 2 in front of water. That gives me 4 hydrogens. Okay, so notice that I'm gonna change the reactants into 4, but by doing that, it also changed my oxygen. So now oxygens, I have 2. Now what I'm going to do is I'm going to add a 2 here in front of lithium hydroxide. So I have 2 plus 2, I have 4 hydrogens. So my hydrogens are going to be balanced. By adding the 2 in front of lithium hydroxide, I also change the amount of oxygens. So now I have 2 oxygens, which is okay because now it's balanced. And I also changed my amount of lithiums. So in that case, I ended up with 2 lithiums. Now, I only have 1 lithium in my reactant, but because I left it until the end, it's easy by just adding a 2 in front of lithium. It doesn't change anything else because lithium is by itself. Notice that my equation is now balanced. And here's the steps I took. Now, before you balance anything, you need to make sure that the chemical equation is correct. For example, if I tell you sulfuric acid and I say it in words, but you don't write the equation correctly, that will throw off the entire balancing equation. So it's important that your naming is on point by now. Like you should know how to name acids, polyatomic ions, ionic molecular compounds, and so on. Here we have another equation. Now, there's something different about the equation is that you're going to notice that you have a sulfate, and that sulfate, it's in both sides. When you have a polyatomic that is on the reactant and it's on the product, I encourage you to leave it together. don't break it apart. So when I'm doing my T chart, I will do reactants and I will do products. My reactants, I will put aluminum, not my reactant, just in general, I put aluminum, hydrogen, and I will do sulfate. Now I count the atoms that I have. So for the aluminum, I have one of my reactants and I have two of my products. For my hydrogens, I have two, and I have two. For my sulfates, I have one and I have three. So what I want to do is I'm going to start by balancing my sulfates. It doesn't really matter what you, at this point. I will start with sulfates because aluminum is by itself, so it's easier to balance later on. I will add a 3 in front of sulfuric acid. That changes my reactant sulfates from 1 to 3, but it also changed my hydrogens from 2 to 6. So my sulfates are already balanced. Now what I'm gonna do is look at my hydrogens. On my reactants, I have 6, and on my products, I have 2. So what if I add a 3 in front of hydrogen on my product size? So that changes it to 6. Lastly, I have 2 aluminum in my products. Because aluminum is by itself from the reactants, I can just add it 2. And now everything is balanced. Always take time to check. Here are the steps that they took. Notice that they left sulfate together. The reason why it was left together is because sulfate is in your products and sulfate is also in your reactants in your product. I said it backwards. So notice that they went through the same steps I did and they come out. It's always good to do a T-chart at the end just to double check that you have everything you need. As I mentioned, when you are balancing an equation and you see an atom such as oxygen alone, leave it until the end. It'll just make your life easier when you are balancing. Here we have another example where you should take your time, do a T-chart, and you will notice that when you balance it, you're gonna end up with the coefficient. You have potassium chlorate, you have potassium chloride, and you have oxygen. When you balance them, you're gonna realize that you're gonna have to put a 2 in front of potassium chloride and you're gonna have to put a 3 in front of oxygen for your equation to be balanced. And always redo the T-chart to make sure everything aligns your products and your reactants. Now, here is this question. Take a minute and try to answer it by yourself. The answer is A. There's another question. Try to see if you can balance it by yourself. And the answer will be putting a 3 in front of sulfuric acid, and you will be adding a 3 in front of water. And notice that in this case, sulfate was left together because it appears in your reactants and it appears in your products. Always double check your T-chart at the end. Here's another equation where pretty much in this case, we're looking for what is the coefficient that oxygen should have when this equation is balanced. So take a minute to try to do it by yourself. And the answer should be 6. Here's more practice. Try to do it by yourself before you seek the answer, which is coming next. The answer should be a 2 in front of aluminum, a 3 in front of bromide. For the second equation, it should be a 2 in front of sodium chloride and a 2 in front of sodium fluoride. More practice. You're gonna realize the more you do it, you're not gonna need to be doing a T-chart because you're gonna be getting used to it. So pause it before you see the answer, which is gonna be a 3 in front of oxygen, a 2 in front of carbon dioxide, and a 3 in front of water. For the second one, you just need a 2 in front of potassium nitrate. Here's another equation for you to practice. Sorry. For this equation, you should only have a 2 in front of potassium chloride. And for the bottom, you should have a 2 in front of water. Notice here, you're gonna have to break hydroxide because it's not on the reactant side. The next one, pause it. Try to do it by yourself. You should have a 3 in front of copper, 8 in front of nitric acid, 3 in front of copper 2 nitrate, 2 in front of nitrogen monoxide, and a 4 in front of water. For the second equation, you should have 2 in front of sodium and a 2 in front of sodium chloride. Another question, pause it, try it on your own. You should have a 2 in front of oxygen, a 2 in front of water. For the second equation, you should have a 2 in front of lithium, and a 2 in front of nitric acid, and a 2 in front of lithium nitrate. The last but not least, you have 2 more equations that you can practice on your own. The first one is kind of easy. The second one is a little bit more complicated. Pause it. Now here's the answer. A 4 in front of aluminum, a 3 in front of oxygen, a 2 in front of aluminum oxide. The last one, which is a little bit more tricky, your coefficients are gonna be 2, 7, 4, and 6. I hope this gives you enough practice for balancing equation. Once you have mastered this topic, we are now going to move on to stoichiometry, when we're going to start doing equations between reactants and products. It is important that you understand and that you master balancing equation before moving forward to the next video. We're going to begin discussing stoichiometry, and as I mentioned earlier, stoichiometry is basically making a numerical relationship between your reactants and your products when you have a chemical equation. So we're going to start doing some calculations when it comes to that stuff. The goal of stoichiometry is going to be able to perform conversions between your units, conversion between your reactants and your products. So we're going to begin by discussing a mole to mole conversion. For example, a mole of the reactant, make it a relationship to a mole of a product. For example, if you have 3 moles of A, how many moles of B you're going to yield? So in order for this to take place, even before you start getting into doing number and doing performing calculations, you want to make sure that your equation is balanced. Never assume that an equation is balanced when I give it to you in an exam or in your textbook or your homework. Do not assume it's balanced. So in order to make this mole-to-mole conversion, this relationship, you want to make sure that your reaction is balanced. And here, for example, the reaction given at the top, it's already balanced. Notice that you have 6 hydrogens on your reactants and you have 6 hydrogens in your product. You have 2 nitrogens on your reactants and you have 2 nitrogens in your product. So what this equation says is that if you have 3 moles of hydrogens, you're going to yield 2 moles of ammonia. And if you have 1 mole of nitrogen along with 3 moles of hydrogen, you're gonna yield 2 moles of ammonia. What happens if I change that? What happens if instead of having 1 mole of nitrogen, I have 3 moles of nitrogen? And let's say you have more than enough hydrogen. So basically what it's saying is don't worry about the other reactant. Let's assume that you have enough. Well, if you have 3 moles of nitrogen, how many moles of ammonia you're going to yield? So the conversion factor that you want to look at it is the conversion factor between ammonia and nitrogen. Now, for every 2 moles of ammonia, you have 1 mole of nitrogen, or for 1 mole of nitrogen, you yield 2 moles of ammonia. So this is the 2 conversion factors. They're equal to each other. All I did was flip it. So let's say which one we're gonna use. Let's see which one we're gonna use. Always start with what it's giving. In this case, you're giving nitrogen. Now, you have 2 options, number 1 or number 2. Which one are you gonna use? Well, since you wanna cancel nitrogen, remember the only thing that you should cancel is nitrogen, and the only chemical that should not be canceled is ammonia, because that's what it's asking. Therefore, you're going to use the first one because you want nitrogen at the bottom. You're going to use that conversion factor. So it turns out that 3 times 2 equals 6 divided by 1 is 6. So if you start with 3 moles of nitrogen, you're going to generate 6 moles of ammonia. Okay? And here's another question where pretty much is the same idea. In this case, you have a combustion reaction. So in this case, you have 2 to 25 to 16 to 18 ratio. Now, what about if you start with 22 moles of this reactant instead of 2? And they're asking you what is the carbon dioxide. So your relationship is going to be between this and carbon dioxide. Everything else for this particular problem can be ignored. So look at the balance equation. It's already balanced. So your conversion factors are going to be 2CH18 divided by 16 CO2, or 16 CO2 divided by 2 CA18. So which one are you going to use? Always start with what it's giving. They are giving you 22.0 moles. That's what they're giving you, right? 22.0 moles of, by the way, that is your gasoline. 22.0 moles gasoline, and they want to know how much carbon dioxide. So since you are starting with gasoline, you want to have gasoline at the bottom. So because it's octane, you want to be able to cancel it. So the one you're going to be using, the conversion factor you're going to be using, is number 2. Your moles of octane cancel, and then 22 times 16 divided by 2, you have 176 moles of carbon dioxide. That's how much you're going to be yielding. This conversion is called mole to mole. You start with moles and you end up with moles. Now we can take it a little bit to the next level where we actually start with grams and we end up with grams. So think about it, we are in 2 more steps. This was a 1-step direction, now we're gonna add it. So here is going to be the map that we're gonna follow. And this, so before I was giving you moles of A to moles of B, but now we're going from mass of A to mass of B. So the way the path you're gonna take is always from mass, always convert to moles. From moles, do a to a mole conversion, and then from moles, go back to mass. So you're adding 2 extra steps. So let's look at an example. Notice here, they're giving you the same equation that we've been dealing, right? We already know that it's balanced. Last time they gave you moles of octane, but now they're saying you have this many grams of octane or gasoline, and they want to know how much your grams of carbon dioxide you're going to yield. So you know the grams of carbon dioxide should be at the top. That's not what you're canceling. So here's your map. You're going to start with that 3.4 times 10 to the 15 grams gasoline. Then you want to convert it to moles. To do that, you know that you're going to have grams of C8H18, and on top you're gonna have 1 mole. Where am I gonna get those the grams? It's gonna be the molar mass. Molar mass. Then you're gonna have a mole to mole relationship. So in this case, you're trying to go to carbon dioxide, which means you wanna get rid of gasoline, so you're gonna have it at the bottom, C8H18, and at the top, you're gonna have the 16 moles of carbon dioxide. Then you don't want moles of carbon dioxide. Notice how I'm canceling everything. But I want grams of carbon dioxide. So what I'm gonna do is put 1 mole of carbon dioxide, and at the top, I'm gonna put grams of carbon dioxide. And those grams are gonna come from the molar mass. And that's the path that you're going to take. So between here and here is molar mass. Between mole to mole is using the balance equation. And between mole to grams is again using the molar mass. And let's see how they solve it. Notice that we started with the grams of that was giving of your octane. This is the molar mass. And 1 mole, notice how I cancel my grams. This comes from the balance equation. And the 4401 is the molar mass. So 3.4 times 10 to the 15 times 16 times 44 divided by 2 times 100. I usually calculate this number first and then multiply the top and calculate it by whatever that number was. So the answer is 1.0 times 10 to the 16 grams of carbon dioxide. Here's a little map that can help you. Notice that every time we go from mass to moles, you use the molar mass. Every time we go from moles to moles, you use the balance equation. Moles to grams, you use the molar mass. And then there's other pathways that we're gonna be taking. We can go from volume, we can go from particles. So that's gonna come later, but it's important that you understand this first. So here's a question for you to try to do it by yourself. So what is the first step? You want to check that this equation is balanced. So how many moles of sodium chloride? So you need moles of sodium chloride. So you know that this is going to end up on top because it's what you want. Results from the complete reaction of 3 moles of chloride. So there you're starting with moles and you're going to moles. So this is a mole to mole ratio, which means it's only 1 step. You want to make sure that the equation is balanced. And it looks like it's not. Now it's balanced. Once it's balanced, they're telling you that you have more than enough sodium, which means you can pretty much ignore sodium in this equation. You start with what it's given, and you want chlorine at the top, at the bottom. This comes from the balance equation. And your final answer is 6.8 moles sodium chloride. This is another question for you to try on your own. Try to do it before I give you the answer. Once again, it's a mole to mole conversion. So here you're dealing with oxygen and water. What they're saying is ignore hydrogen, but before you ignore it, balance the equation. So the first step is balance the equation. I hope you came up with the answer. And the answer should be 8 moles of water. There's another equation for you to try by yourself, making a relationship between ammonia and hydrogen. Be sure to balance your equation first. This is still a mole to mole equation, so that means it's only one step pretty much. Here's your answer. Now the upcoming one, it's a little bit more difficult because now you want mass of hydrochloric acid. So, and you're dealing with aluminum. So you're starting with 6 moles of aluminum and you 1 grams of hydrochloric acid. What that means is in this case, you can ignore the products. But before you do it, first balance the equation. Then what you're going to do is to go from moles of aluminum to moles of hydrochloric acid to grams of hydrochloric acid. So from moles to moles, you're gonna use the balance equation. And from moles to gram, you're gonna use the molar mass of hydrochloric acid. And here's your answer. Another practice problem. In photosynthesis, plants convert carbon dioxide and water into glucose. This is the equation for glucose according to the following reaction. Once always make sure is this equation balanced. This equation is not balanced. You should have a 6 in front of carbon dioxide. And you should have a 6, I believe, in front of water. If I'm not mistaken, you should have a 6 in front of water. A 6 in front of water, that gives me 12. Yeah. Okay. So now, excuse my puppy. So you're going from grams to grams of glucose. No, that's how many you want grams of glucose, but you're starting with grams of carbon dioxide. So now you want to make, so this one is going to be more steps. You started, notice this is the molar mass. This is the balance equation. This is the molar mass of glucose and your final answer. Here's another practice problem. Be sure to balance your equation first. And here's your answer. These are good practice questions. Last but not least, this is going to have an extra step. Notice that the equation is given to you. They want to know how many milliliters of water are made in the combustion of 9 grams of glucose. So pretty much you're going to go from 9 grams of glucose, and then you're going to convert it to moles of glucose. Then you're going to go to moles of water. Then you're going to go to grams of water to milliliters of water. So from grams to moles, you're going to use the molar mass of glucose. From glucose, moles of glucose to moles of water, you're going to use the balance equation. From moles to water to grams of water, you're going to use the molar mass of water. From grams of water to milliliters of water, you're going to use the density of water. Once you try it on your own, move on to the next slide where the answer will be provided for you. We're going to switch topics a little bit, and some of the questions have said you have more than enough of one of the reactants. Well, when you have a reaction, you're gonna have different reactants. Some of those reactants are not gonna be in the same amount. Some of them are gonna be less than others, and a specific reactant is going to determine, especially the one that you have less of, is going to determine how much product you're going to yield. So just to give you an example, if you have 3 tires for a bicycle, and I ask you how many bicycles can you make, even though you have extra parts for everything else, your answer will only be 1, because the tires that you have limit how many bicycles you can make. So the tires in this case will be considered your limiting reactant. It will be the reactant that limits how much product you can make. Now the limiting reactant is the one that is completely going to be consumed. The rest of the reactants, the other parts, are going to be considered excess reactants. The limiting reactant, and this is very important, the limiting reactant is going to determine the theoretical yield. So we're going to go through an example to kind of help you explain all these terms. Even though we come out with a theoretical yield, things don't always go as planned, especially in your lab. Sometimes you are synthesizing a reaction and your lab partner comes and blows something up. So now you had less than what you anticipated. So that is actually called the actual yield, whatever you actually came out when you finish your experiments. Usually the actual yield is going to be less than 100%. The reason being is that we always make mistakes in lab. You shouldn't end up with more than 100%, but things happen. To figure it out how efficient you were in your experiment, we're gonna calculate the percent yield by using the following equation. Percent yield equals actual yield divided by theoretical yield times 100. So let's go on a little experiment. This is the recipe to make 5 pancakes. In our world will be the chemical equation. So this is a recipe. What it says is if I have 1 cup of flour, I'm going to yield 5 pancakes and so on. But let's say in this experiment, I have 3 cups of flour and 10 eggs and 4 teaspoons of baking powder. How many pancakes can I make? Well, if I had 3 cups of flour, I'm gonna generate 15 pancakes. If I have 10 eggs, I'm gonna generate 25 pancakes. And I have 4 teaspoons of powder, I'm gonna generate 40 pancakes. Now, which of these ingredients is the limiting reactant? The one that made the least. That will be your flour, will be considered your limiting reactant. The reason for that being is it doesn't matter that you have 10 eggs and have all of these extra ingredients. If you do not have enough flour, you're not going to be able to make those pancakes. So your limiting reactant is going to be your flour. Therefore, your theoretical yield will be 15. Those are the maximum pancakes you can make with the ingredients that you have. Okay. So with that being said, let's say that you actually, okay, you have all of these ingredients, you start cooking, but then things did not go as planned. You burned 3 pancakes and 1 fell on the floor. So how many pancakes did you actually make? You made 11 pancakes. So this will be your actual yield. In order to calculate the percent yield, we will do your actual divided by your theoretical yield times 100. So in this cooking experience, you were only 73% successful. Keep in mind that the actual yield in a chemical reaction must be determined experimentally. So in an exam or in a homework, I will be giving you this number. The actual yield is always less than 100, just because things happen in the lab. Here we have another question, so for you to practice. So let's say I give you this equation and I tell you I have 53.2 grams of sodium and 65.8 grams of chlorine. Which one is the limiting reactant? So one of these two is the limiting reactant. We can't just say it's sodium because you have less grams. No, you actually have to calculate the math. You have to do stoichiometry. So one, make sure your equation is balanced. In this case, your equation is not balanced, so you have to balance your equation. You put a 2 in front of sodium. Chlorines are balanced. Okay, so now we're balanced. So you want to start with your grams. So you're trying to go from sodium, grams of sodium, so grams of sodium, to moles of sodium, to moles of sodium chloride, to grams of sodium chloride. So once again, this is the molar mass. This comes from the balance equation, and this comes from the molar mass of sodium chloride. Notice that if you have 53.2 grams of sodium, you're going to generate 135 grams of chlorine. However, if you have 65.8 grams of chlorine, you're going to generate 108 grams of chlorine. Because that chlorine gave you less grams of sodium chloride, chlorine is your limiting reactant. Therefore, the least amount of product becomes your theoretical yield. Theoretical yield. That will be your theoretical yield. Now, how do we calculate a percent yield? Well, I will have to tell you the actual yield. So we already know, so I'm telling you that the actual yield is that theoretical yield is what we calculated from the previous part. So your percent yield is 80%. That's how successful you were. So let's try to do one by ourselves. So notice that in here it has a reaction. And let's see if it's balanced. It's not balanced. Now it's balanced. So it says, what is the limiting reactant? So you're trying to see how much of this can I make if I start with 42.5 grams of magnesium. So what am I going to do is I'm going to convert these grams of magnesium to moles of magnesium. So this number 2431 is the molar mass. 1 mole of magnesium. Notice that my magnesium is canceled. Then looking at this, for every 2 moles of magnesium, you're going to generate 2 moles of magnesium oxide. Now, you don't have to keep going to the grams in order to determine the limiting reactant. You can stop at the moles. So for example, on this slide, notice that if you stop here, you see which moles are less. In this case, the magnesium gave you the less amount of moles, which means that your magnesium must be your limiting reactant. Now, to find the yield, you actually have to go to grams. So what we do is we take the least moles and do the extra step and convert it to grams. So therefore, 70.5 is going to be your theoretical yield. Theoretical yield. Notice in the previous slide, it tells you that it yields. This word yields, that means that you produce. So that 55.9 is going to be your actual yield. So when to calculate the percent yield will be 55.9 divided by 70.5 times 100. That will give you your percent yield. Here's another question for you to try it on your own. We can always do it together later on, but it's important for you to try it on your own. And here's your answer. Notice that you started with different amounts, but because copper 1 oxide gave you the least amount of product, copper 1 oxide becomes the limiting reactant, and the 101.7 becomes your theoretical yield. Notice that it says that yield, so this one is your actual yield, which we're going to need in order to calculate your percent yield. Here's another question for you to try on your own. Always be sure your equation is balanced. This question is just asking how many moles, so you don't even have to go to grams. They just want to know how many moles of methanols you're going to be able to produce. Here's your answer. So the limiting reactant is going to be hydrogen because it gave you less product. Notice that for this to work, you need to make sure your equation is balanced. If your equation is balanced, you're not going to have accurate results. Here's another question. This is going to be similar to what you're going to have on your exam. Here's your answer. So in this case, iron is going to be your limiting reactant because it's the one that is giving you less of less product. Here's another question. And here's your answer. One more practice problem. Notice that in this case, you are starting with 1.75 grams of salicylic acid and you have excess methanol. So in the case that this is methanol, this is excess, it is already telling you this is the limiting reactant because you have excess of methanol. So now what they're saying is that you are going to, it reports the production. So this will be your actual yield. So all you need is convert these grams to moles of C7H6O3 to moles of C8HAO3 to grams of CaHAO3. And that will give you your theoretical yield. Which is going to be 1.93. And now you can calculate your percent yield, which is 73.6. So practice this before we actually move on to the next section. So this should be enough on this topic. And then we're gonna start looking at concentrations. Welcome back. We are now going to continue with the next topic in this chapter, which is how to describe a solution. So a solution is going to be something that is liquid type, and it has a mixture. So a solution is a mixture. 99% of the cases, that mixture has water. So how do we describe it? We're gonna use words such as concentration and so on. So before we get started, let's go over what a solution is. A solution is a homogeneous mixture, which means it is gonna be very difficult for you to see that there is a mixture. You're not gonna be able to see physically, you're not gonna be able to see the different phases, but you know it's a mixture. For example, let's see, a coffee latte, it's a mixture because it has milk and it has coffee and it has water. So those are a juice, it's a mixture. It's a homogeneous mixture because you know that it has water, orange, or whatever kind of juice you're drinking. Now, in a solution, it's going to be composed of a solvent and a solute. So the solvent is the one that is doing the dissolving, is the one that you have more of. Most of the time, is the liquid. Not 100% of the time. Most of the time, it's the liquid, and it tends to be water. The solute is the one that is being dissolved by the solvent, and it's going to be the one that you have less of. These solutions that have water are considered aqueous solution, and we're going to represent it by AQ, meaning that it has water in it. It's being dissolved in water. So when you see the AQ, that's what it means. So as I mentioned, we're going to be describing the solutions, and we're going to be using basically different terms, and we're going to be, like, in order to compare them, we're going to have to using these terms. For example, when you have more solute, then you have solvent, we say that is concentrated. So we're going to be looking at the kind of composition that this have. For example, salt water samples from different seas or lakes have different amount of salt, different amount of solutes, which means one water may be more concentrated than the other. So in order to be able to describe this, we're going to be using terms such as diluted or concentrated. So these are going to be qualitative solutions are often described as diluted or concentrated. So a diluted solution is when you have a homogeneous mixture and you have more solvent than you have solute. So think of it as when you have a very, very light coffee that you really don't taste that strong caffeine. In my opinion, decaf, that's waste just period. Like, why people drink it. But so that's the idea. A concentrated solution is when you go to your closest or your favorite coffee shop and you ask for straight shot of caffeine, and sometimes you just mix it with a little bit of milk. You have it concentrated. What that means is that you have a large number of solutes compared to solvent. Or when you go to the bar and you have a double whatever drink that you may favor, they just put they just make it more concentrated. So when it comes to this whole idea of concentration, we actually are going to start putting numbers of it. And even within concentration, we have different ways of describing different units of describing concentration. We are going to touch one in this chapter, which is the most common, but later on, we're going to describe the many other ways that we can describe concentration. Basically, different units that we can use to describe concentration. And here, we're going to be discussing molarity, which is going to be capital M. Molarity, every time you see capital M, it means moles, the amount of solute, and this has to be in moles, divided by the amount of solution. It has to be in liters. So M equals this. Always make that relationship. And also you can make it as 1 liter over, moles, right? Because this is the definition of molarity. Since it's a definition, we can use it as a conversion factor. Now, every time you see M, I need you to make that relationship to be, if it makes you, I think what you need to do is that every time you do M, immediately change it to moles per liter. So you can understand what that means. When we are, so for, let's say I ask you to prepare in lab, I ask you prepare me 1 liter of this concentration. So what I'm going to do is I'm going to focus on the 1.0 molar. So I'm going to switch it just like I told you. But first, let's start with what it's giving. So let's switch it. So 1.0 moles over liters, or 1.0 liters over 1 mole. So that's what this means. This is what that means. And you want to make this relationship. Now start with what it's given. You have 1 liter. Now what are you going to do? You want to get rid of your liters, because eventually it says how to prepare it. So you know that you need to make 1 liter and you don't need to dissolve it in water, but how much sodium chloride do we need? So we want to cancel the liters, and you want to use that one because liters cancel. So you have 1.0 moles over 1 liter. You cancel your liters, and this is NaCl, but we can't go in lab and measure 1 mole. So we need to convert it to grams. And to do that, you're going to use the molar mass. So 1 mole of NaCl, I believe is, if I'm not mistaken, 58.44 grams of NaCl. Notice that your moles cancel and you end up with 58.44 grams of NaCl. So what that means is that you're going to grab a volumetric flask and you're going to add your 58.44 grams of sodium chloride, and then you're going to have that line that you see here that represents 1 liter. You're going to add water up to that mark. Once you do that, you have completed completed the process of making that solution. Okay? All right, so let's try to do an example. Notice here it says find the molarity. So that means that they're asking you to find M. Remember, M equals moles over liters. So you need to end up with those two units. In this case, they are giving you grams and they are giving you the liters. Now, you need moles. So what you're gonna have to do is you're going to have to convert those grams to moles. So you convert those grams to moles. Once you have your moles divided by the liters that we're giving, and you have moles over liters, which is the same as molarity. And since you were given three significant figures to begin with, your solution should be in three significant figures. So as I mentioned, because molarity is going to be a definition. The definition of molarity is moles over liter. We can use it as a conversion factor. So depending what we need, you can either use it moles over liters or liters over moles. Here's a practice question. Notice this is calculate the molarity. So you need to end up your moles over liter. They are giving you the moles and they are giving you milliliters. So what do you need to do? Convert that to liters. So give you a chance to do that. Your answer for this question should be 4.04 molarity or 4.04 moles over liter. Here's another question. Now be careful because this is giving you the molarity and it's giving you milliliters and it's asking you for moles. So when I see this, I automatically am going to convert it to this. Or and you want to start by what it's giving you, but from here it looks like I have to go from milliliters to liters. Once you do it, your final answer should be 0.200. Try another one. This one is asking for how many grams. Once again, they are giving you the molarity and they are giving you milliliters. So that it's a little bit step further than the other one. So remember, you're going to convert this to 2.10 moles over liter or 1 liter, 2.10. Convert this to liter. You're gonna need the molar mass, KCl. Once you finish, your answer should be 8.61 grams. Here's one more practice. Your answer for this should be 0.224. Okay, so that should give you comfortable with molarity. Now, often we have a solution that is given to us very concentrated and we need to dilute it. So we are going to be doing dilution calculations. And a stock solution is pretty much the original solution, the concentrated solution, the strong solution. And basically you're gonna have like 10 molarity or whatever. So it's the concentrate. So that's gonna be the initial one. So it's gonna be higher. Now, when we wanna dilute it, we are going to be adding more solvent. Usually the solvent tends to be water. When you do that, the amount of solute does not change, right? Because if you go to the coffee shop and you ask for 3 shots of caffeine, the amount of caffeine does not change, but what changed is the volume because you added more water, okay? So another point is that concentration and volumes of the stock solution and new solutions are inversely proportional. What does that mean? That if you have as the concentration, so here is the stock, okay, concentration, and this is the new solution, new solution. So as the volume of this goes down, the volume of the new solution will go up. And the concentration, the same thing as the concentration. This one is high, this one is gonna be low. The way to put it together is by using M1V1 equals M2V2. That is going to be the equation. So M1 represents the stock solution, the original. So this is stock. M2 represents the concentration of the new solution. V1 represents the concentration of the stock solution. Sorry, the volume of the stock solution. V2 represents the volume of the new solution. So for example, if you went to get coffee and let's say your concentration of your coffee was 10 M and you only had, let's say you had 50 milliliters and you think it's too strong. So what you want to do is you want to add water to double it to make sure that your volume now it's going to be 100 milliliter. So notice that it's inversely proportional. As the original goes down, the volume of the new one goes up. Same thing with the molarity. So the molarity, because now you have more water, it's probably gonna go down to 5 M. So inversely proportional, that's what that means. Now, when we use in this equation, make sure that we're dealing only with one solution. If you start mixing it, for example, if you have coffee and you want to mix it with orange juice, just, I know this sounds disgusting, but if you have those two solutions and you want to mix it, you can't use this equation because now your solute is actually going to change because there's other stuff in it. So we don't want to use that. Only when, for example, you have something strong such as coffee and you add in just plain solvent, plain water. That's when you use this equation. Here it's a question that will show you, that gives you an idea how you will use this equation. So it says prepare 5 liters of a 1.5 molarity KCl from 12.0 molar stock solution. So the word stock solution tells you that this is M1 and the 5 liters with the 1.5 molar KCl, this is your new solution. So this is gonna be your M2 and this is gonna be your V2. In here, you're solving for your V1. We know that your V1 must be less than 5 liters because they're opposite, right? They're inversely proportional. So what you're going to do is take this equation, manipulate it in order to solve for V1. Once you manipulate your equations, all your units, notice how they're changing it M. They automatically change it to moles over liter. All your units should cancel except for liters. And what that means is that now you're going to be adding the 0.625 of your, so this is V1, M1, and when you finish, you're gonna generate 5 liters, which is your V2, of 1.5 moles molarity KCl. Here's another example for you to try. Notice that in here is asking you what volume should you dilute? So that's telling you you're looking for V2, Notice that they're giving you B1, M1, and M2. So in this problem, you're actually looking for B2. Take time to read the problem and be sure to understand what's your B1, what's your B2. Here's an example for you to try on your own. Once you finish, your answer should be 21.9 milliliters. Here's another one. Your answer should be 8.24 molarity. Okay, as I mentioned, the M1V1 and M2V2 equation is only going to be used when you have on one solution and you're just adding water or solvent to dilute it. What happens when we're dealing with two things? So if we're dealing with orange juice and we're dealing with coffee. How do we do that? Well, in that case, you're going to be using stoichiometry. So for example, if this is your coffee and you're mixing it with your orange juice, what you're gonna do is go from volume of coffee to moles of coffee to moles of orange juice to volume of orange juice. So you're gonna be using stoichiometry. In order to do that, you're going to need a balance equation. And this idea is on the exam, so you wanna make sure that you understand it and request more help if it's needed. Notice here it's asking you what is the volume of, okay, so they're giving you a concentration. Automatically, I will say 0.150 moles over liter. So that's your M, right? Molarity is required to completely react with 0.15 liters of 0.175 moles over liter lead nitrate. I see two solutions. So the M1V1, M2V2 automatically ignore it. In the reaction they're giving you, your reaction, want to make sure that your reaction is balanced. Once your reaction is balanced, you're going to start with one of the solutions. And I usually start with the one solution that I have the volume and concentration. Notice that for the first one, KCO, you only have the concentration. And it's the one that we are seeking for. So whatever you're looking for information about potassium chloride. So you want to end with that. So what we're going to do is we're going to start with what it's giving, and you're going to start with 0.150 liters of lead 2 nitrate. Then you're going to use its concentration in order to cancel your liter. So remember that this is 0.175 moles over liter, or 1 liter divided by 1.175. You want to use the one where liters end up at the end, 0.175 moles of lead. So notice here, now you have lead, moles of lead, but you are seeking for potassium chloride. So from here, you're going to use the balance equation to make a relationship between lead and potassium chloride. So that relationship is 2 to 1. So you're going to have, at the bottom, you're going to have lead nitrate, because that's what 1 mole of lead nitrate, because you want to get rid of that, and 2 moles of KCl. Notice that now it cancels. Now, what other information do I have? Well, I have the molarity of KCl, so you want to use it. And remember that it's 2 ways to use it, either liters and 1.5 moles. So which ones do you want to use? You actually want to use the second one in this case, because you want to be able to get rid of your moles. When you do that, notice that what cancels is your mole of KCl, and you end up with liters of your solution. So here's the answer. So notice that, notice, cancel, 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 cancel. And this question will be on the exam, something like this. So you want to make sure that you understand the concept. It's important to have a balanced equation because if it's not balanced, these two numbers are not going to be correct. And it's going to throw off your entire problem. Notice how it's another question. Same idea. You go from, you're going to start from the one that they give you, that molarity and the volume. So start with that information. Then you're going to go from moles to moles, which is the balance equation. And then you're going to use the concentration of the solution that you're looking information from. Here's another problem for you to try it on your own. Be sure that the equation is balanced. Once you finish your answer, and this is a good question for you to try on your own. Should be 9.38 milliliters. If you can't do this, let me know so we can do it together. The next practice question will be that one, the one on the screen. The answer will be 6 liters. Okay, so that pretty much talks about the solutions and how we're describing them. We are going to move forward with the next topic. For right now, I think this is a good stopping point. I'll see you soon. Okay, we are going to continue our discussion, and now we are going to still be discussing aqueous solutions, and we are going to see how they dissociate when they are put in water. Now, it's important for us to know the difference between ionic compounds and molecular compounds. For example, salt is an ionic compound. Since it's an ionic compound, it will dissociate into sodium and chlorine. Water, it's a molecular compound. It will not dissociate. Same thing with sugar. It's a homogeneous mixture. When you stir it, as you stir those substances, it seems like it's disappearing. The sugar is disappearing, but it's not really disappearing. Pay attention to this slide. When you dissolve sodium chloride in water, your chlorine is going to be attracted to the hydrogen, which has a partial positive charge, because opposites attract. And the sodium is going to be attracted to the chlorine because the sodium carries a positive charge. And the chlorine carries, the oxygen in the water carries a negative charge. So it's going to be pulling apart that sodium chloride. So in order for that solution to be formed, you need to break your solute, which is salt. That interaction, it needs to be broken, and you need to form a solvent-solute interaction in order for you to have a solution. We are going to be discussing this further later on, but for right now, we just want to show you how it was going to be dissociating. Now, when you have ionic compounds, what's going to happen is you're going to separate it, you're going to be separating those ions. So it's going to be pulling them away from the crystals. When the ionic compound enters the solution because they're going to be surrounded by water, and then what's going to happen is now you're going to have free charges flowing around, which have the ability to conduct electricity. So whenever we have substances that dissociate into water and they have individual charges, we call those substances electrolytes. And the reason why they are called electrolytes is because they have the ability to conduct electricity. So materials that dissolve in water to form a solution will not conduct electricity. Those are called non-electrolytes. So this will be your molecular compounds because they don't dissociate. They don't, the sugar will stay together. It will dissolve in water, but it will stay together. A solution such as salt, which is an ionic compound, will conduct electricity. It's considered an electrolyte. So more on molecular compounds. In order for a substance or material to conduct electricity, you must have charged particles that are going to be freely floating around. Electrolyte solutions all contains ions. Remember, the word ions means charge, dissolve in water. So ionic compounds are electrolytes because they dissociate into ions. They separate into ions. Non-electrolytes, such as molecular compounds, they dissolve in water. So generally what happens is molecular compounds do not ionize, do not separate. When they dissolve in water, they kind of stick together. The only difference, and there's an exception, the exception will be acids. Acids are electrolytes. Acids are electrolytes. Okay, notice here we have two images. We have when you have ionic compound, which is salt, notice how it's separating the ions. So you have floating charges. In here, the second image is showing the sugar is being surrounded by the water, but it's not separating the water itself. Acids, because the protons, remember that acid starts with an H, the proton gets ionized, it comes off. So therefore, you're going to, when hydrochloric acid dissociates, you have floating charges around. So a strong acid equals a strong electrolyte. A weak acid, and it's indicated by this double-headed arrow, it's a weak acid is considered a weak electrolyte. Strong acid, strong electrolytes, weak acid, weak electrolyte. A strong electrolyte, that means that it will fully dissociate that proton, that H. So proton and hydrogen, we use them interchangeably. It's going to come off 100%. In a weak acid, it won't. What that means is that you're going to have some of this in the solution, you're going to have some of this in the solution, and you're going to have some of the original compound. In a strong acid, you're only going to have chlorines and hydrogens floating around. So weak and strong electrolytes. Stronger electrolytes are going to be those substances, those materials that are going to dissociate completely into ions. So those are your ionic compounds, and your strong acids, they're going to conduct a lot of electricity. Weak electrolytes are those that partially dissociate into ions. Those are going to be your weak acids, and some ionic compounds we will see later on which ones they are. When a compound has a polyatomic ion, notice that when it dissociates, that polyatomic ion will stay together. See here, here's your sodium and here's your sulfate. Notice here, this is acetic acid, here's your hydrogen, and here's your acetate. When you put the substances in and you put an electrode, notice that the electrode is gonna cause the light bulb to go on. When you have sugar, because it's a molecular compound, it's a non-electrolyte, it won't cause, there's no current passing through, so there is no electricity, that light bulb won't light up. Notice here we have acetic acid, which is a weak acid. It's partially dissociating, so it will partially dissociating, so it will go ahead and give you a dim light. And sodium chloride, because it's an ionic compound, it's going to be a strong electrolyte. It will dissociate completely, and we're gonna have a lot of current. We're gonna have a strong light. When we have ionic, not all ionic. So remember, ionic compounds dissolve in water. Well, not all ionic compounds are going to be soluble in water. Some ionic compounds are going to be non-soluble in water, insoluble. For example, ionic compounds like sodium chloride dissolves very well in water at room temperature. And we're saying at room temperature because temperature will affect solubility. On the other hand, we have silver chloride. At room temperature, it won't dissolve. So when they dissolve in water, we call them soluble, and we represent it with an S. Sorry, aqueous. We represent an aqueous because it dissolves. When it's insoluble, we put solid, meaning that it precipitates. There's a solid in solution. Now, there is also some compounds that have a degree of solubility depending on the temperature. As you increase the temperature, solubility will increase. But how do you know which compounds are going to be soluble in water and which ones are not? We have what is called an empirical method, which is pretty much just running experiments and trying it. Obviously, we don't have we have too many compounds and it will take forever. So instead, there is a set of rules that we go by to kind of figure out what's gonna be soluble and what's not gonna be soluble. For example, this chart, it's saying that these compounds are going to be soluble except when you mix them with this. So for example, lithium chloride, if you do lithium chloride, will you say it's soluble or insoluble? Well, lithium, it's here, says that it's soluble and it doesn't have any exception. So I will write aqueous. Potassium chloride will be aqueous because potassium is there, but it doesn't have any exceptions. Now, nitrate, same thing. So if I do potassium nitrate, well, nitrate, it's in here and it doesn't have any exception, so it will be aqueous. Chlorine, bromines, and iodines is soluble except in the presence of this. For example, if you do potassium chloride, well, chlorine is here and potassium is not one of the exceptions, so I will write aqueous. However, if I do silver chloride, well, chloride says it's soluble except when you mix it with silver, so I will put the letter S, saying it's insoluble. Same idea with sulfate, is soluble except when you mix them with that. So for example, silver sulfate will be solid, insoluble. Calcium sulfate will be insoluble. Strontium sulfate will be insoluble. However, if I do potassium sulfate, well, here sulfate, potassium is not one of the options, so I will say aqueous is soluble, okay? Now here's another chart with the opposite. These compounds are generally insoluble except when you mix them with this. For example, let's say calcium hydroxide. Hydroxide is here, so they're saying it's insoluble, but calcium is not here, so this will be solid. But potassium hydroxide is insoluble, but when you mix it with potassium, will become soluble. For right now, ignore the part where it says slightly soluble. When you get to the next level of chemistry, you will understand what that means. So assume the slightly soluble, that means insoluble. The chart that you will be provided on the exam is this one. So you want to become familiar with this. Make sure you know how to use it. These ones are soluble except when you mix them with this. These are insoluble except when you mix it with those exceptions that is provided for you. which brings us to looking at precipitation reactions. So we're going to be looking at different types of reactions. One of them is precipitation reaction. Precipitation reactions are pretty much when your reactants are aqueous, and when you mix them, they precipitate, they give you a solid. So that product that comes out that is solid is considered a precipitate. Here we have an example where we have, it doesn't show, we have your reactant, which is aqueous, and the second reactant that is aqueous. When these two were mixed, you form a precipitate, which is solid. If you look at the table, lead with iodine, when they go together, they form an insoluble compound. Sometimes you're gonna see that when you mix aqueous with aqueous, you're going to form an aqueous and an aqueous. When that happens, we say that the whole reaction was formed because you really don't see any solid. So we say the reaction did not take place because how do we know that there was actually an exchange of ions? Okay, so the way you're gonna be tested with this is you're gonna give names and you're going to be giving those reactions. You're gonna be able to predict. So determine the ions which are aqueous. Most of the time they're gonna be aqueous, and make sure that if the name is given, you know how to write it correctly. Determine the formula of the products. Determine the solubility by looking at the table, and so on, and balance the equation. So let's go over an example before we do anything else. If I give you, I tell you your reactant is potassium iodide and potassium nitrate. Wait, potassium iodide and potassium iodide and lead nitrate. And lead nitrate. And lead 2 nitrate. Those are your reactants. I will be giving you that. You're gonna have to look at the table and see that they're both aqueous. Okay, first thing. Now, how do you predict the products? The way you're gonna predict the products is by separating them into ions. So the potassium carries a plus charge, the iodine carries a negative charge. The second reactant, you're gonna separate it into lead, which carries a 2 plus, and nitrate, right? So what you're going to do is you're going to mix the cation of the first reactant with the anion of the second reactant. Cation of the second reactant with the anion of the first reactant. So when you do that, and always put the cation first. So notice that lead 2, so you have lead, so separate them, lead and iodine. So then crisscross, which I taught you on the previous experiment or previous chapter, PbI2. Then for potassium, just bring it down, potassium K plus, and then nitrate, which is NO3 minus, potassium nitrate. The next thing is to kind of look at the table and realize which one is soluble and which one is insoluble. So the question that you'll be giving, and I will go through this, it's like this. Let's say you have this on the test. So it's coming up, but I will do it for you. Write the equation, precipitate reaction, solution of potassium carbonate. Okay, this is one of my reactants. And nickel 2 chloride. So first, what is potassium? K plus, because it carries a negative plus charge. And what is carbonate? You have to remember what carbonate is. So carbonate is CO3 2 minus. So then you want to put that together. So it's going to be potassium. Oh, I'm going to write it here. Potassium 2 carbonate. And then looking at the table that was previously, you're gonna realize that this is an aqueous compound. Okay, so you finish the first one. Then move on, might erase this, and it says that you were giving nickel chloride, nickel 2 chloride. So nickel, Na plus 2 plus, chloride negative. So you want to crisscross, and it looks like you have nickel Cl2. And if you look at the table, you're gonna realize that it's aqueous, okay? Now you have to figure it out your products. How do you figure it out your products? So how do you figure it out their products? So what I'm gonna do is I'm gonna separate and I'm gonna put on top of another. So look, potassium plus carbonate 3, 2 minus, and then the other compound is nickel 2 plus and chlorine minus. So what I'm gonna do is potassium goes with chlorine, nickel, because it's the cation, is going to go with carbonate. And I will write them on the side so I can know what I'm doing. So nickel 2 plus and carbonate 2 minus 3. So you want to crisscross, and what that's going to give you is nickel CO3. So that's my first product, nickel CO3. Then look at the solubility, and you're going to see that in this compound, because it has the carbonate, it's actually going to be insoluble. So we're going to put an S. It doesn't matter which one you do first. What I'm going to do next is bring my other one. So my cation is potassium and my anion is chlorine, crisscross. And I'm gonna do potassium. Always put the cation first, potassium chloride. And that's going to be my other product, potassium chloride. And this, according to the table, is soluble. So we're gonna write aqueous. The next step is just check that your equation is balanced. And it looks like if you added 2 here, that should be balanced. So this is what you should be able to give me. And this is the first part. There is more to it. So I'm going to show you the answers. Oh, let me erase this. So here's the answer. So first, predict your reactants and the phases. Predict your possible products by crisscrossing them, exchanging them. Then predict which one is the solubility. And then balance your equation. And that's your final answer. Now, this is considered the molecular formula. That's what we call it, the molecular formula. So the molecular formula is the one that describes the state, and it's a balanced equation. So notice here, this is your molecular formula. Now, we also have what is called a complete ionic equation. So this is when we take the molecular formula and we dissociate it into individual species, into individual atoms. So in here, you have to remember, so for this to work, for you to do the complete ionic equation, your phases, your states have to be correct. If they are wrong, they are going to make your whole equation wrong. So notice how we took, so how do I do that ionic equation? What I'm going to do is I'm going to separate everything except my solids, my liquids, and my gases. So notice what I'm gonna do. I'm gonna do it in blue. So I have 2 potassium. So I'm gonna write 2 and I'm gonna write K and it's going to be plus. And since this compound is aqueous, that means my potassium is going to be aqueous too. Then I have hydroxyl. If it's a polyatomic, remember, leave it together. So I have 2 hydroxyls. That 2 counts for the potassium and for the hydroxyl. So I'm gonna write 2 hydroxyl, and you wanna put the charge of hydroxyl, and it's also aqueous. Plus this is aqueous, so that means I'm gonna separate it. I have 1 magnesium, so I'm gonna write Mg, and what is the charge of magnesium in that compound? It's a 2 plus, and it's aqueous. Then what I'm gonna do, notice what I'm gonna do here, oops, and this is important, that I have 2 nitrates. So this 2 is actually going to become a coefficient 2 nitrates, NO3 negative, and I'm gonna write aqueous. Then you move on to your products. It's aqueous, so I'm gonna do 2 potassium plus aqueous, don't forget the states, plus 2 nitrates, aqueous and with the charge, okay? Then you move to the next one, which happens to be a solid. A solid, we are not gonna separate it, so I'm just gonna write plus, the answer will be MgOH2 solid. And this is your ionic equation. Here's your answer. Now, after the ionic equation, we have what is called the net ionic equation. The net ionic equation pretty much removes everything we did not use to make your magnesium hydroxide, or in easy terms, anything that shows up on both sides. So for example, you're gonna cancel anything that shows up on both sides. For example, nitrate, here's nitrate, here's nitrate, you cancel it. Potassium, here's potassium, here's potassium. Everything else, all you do is bring it to the bottom. So those that we cancel are called spectator ions. Notice that we cancel and then we just bring everything down that we did not cancel, and that's considered your net ionic equation. Your net ionic equation. So we also have what's called neutralization. So that was precipitation reactions. We also have neutralization reaction, which is when you have an acid and a base mix. So here is your acid and here's your base. When they mix, they always generate a salt and water. This is always going to be the case. The net ionic equation of an acid and a base will always be the same. Okay, so this is a little bit of acids and bases, which we're going to discover later. In an acid, it ionizes in water, and what happens is going to generate this H+. But because in that solution, we always have water, what's going to happen is the H+ is going to get with that water and it's going to form hydronium ion. Hydronium and H+, we use them interchangeably just because for every H that you have, it's going to get together with the water. Bases are going to dissociate and are going to generate this hydroxyl. Not always, but you're going to have the hydroxyl, which indicates you have a base present. Whenever you have a base and an acid, you're going to generate a salt and a water. I know you're not familiar with acids and bases, so here's a list so you can start becoming familiar with the acids. But the one thing the acids have is that they all start with H, and that's the H that is going to come off. Notice here we have common bases. Most common bases for you right now are gonna have the hydroxyl, or it's gonna have this carbonate, hydroxyl or carbonates. And another special one that you have to memorize is ammonia. Ammonia is a base. Notice here we have the acid and base is dissociating into salt and water. Here's an example for you to try. Notice that it's asking you to write that molecular, and this is exactly how you're gonna have on the test, molecular, ionic, and net ionic. So first, you wanna make sure that you know what a nitric acid is and what you know what calcium hydroxide is. That's the first task that you need to do. Those are your reactants. They're both aqueous. So once you have developed your reactants, you want to predict your products. Well, you know you have an acid and a base, so you automatically know you're going to have water. So you have your possible products are going to be your salt and your waters, following the same method that I taught you. It's going to take a minute for you to kind of like get the hang of it. Once you have done that, you want to balance the equation. Balance the equation. And then dissociate everything for the net ionic equation. You want to dissociate everything. Every time you see water, put an L, it's liquid. You're going to dissociate everything except for water. Once you balance the equation, this is the balanced equation. So now you're gonna get the ionic equation. So this is the molecular. This is the molecular equation. Now you're going to have your ionic equation. So you're gonna dissociate everything except for this. Notice how we dissociated from the molecular equation. So this is your net ionic. Your ionic equation. To get the net ionic, you're gonna cancel everything that appears on both sides. And from there, you get your net ionic equation. Always reduce it. Remember, you wanna reduce it, so since everything has a 2, just reduce it. Here's the practice. Notice that in this case, I'm giving you the the reactants. Go ahead and try to give me the products. Take your time to do it. And here's your answer. There is one more type of equations that we need to talk in this video, and that's going to be your gas evolution reactions. Right now, you have learned that if you're given 2 reactants, you're going to form 2 products. However, in a gas evolution reaction, you're going to have a gas that is formed. So you're going to end up sometimes with 3 products or just a gas itself. So mainly most gas evolution reactions are going to be whenever you have an acid and a base. So you want to pay attention if I'm giving you an acid, and I 100% I'm going to give you a gas evolution reaction on the exam. So you want to make sure that you pay attention of what reactants are being given. When a gas, for example, in here, notice that you're going to see that you end up with a sulfide, and then that forms a gas. So because I gave you an acid and I gave you a base. At this point, I don't think you know that that's a base, but it's okay, I will be telling you. So notice that you are giving a gas. You're gonna result in a gas. Notice here you have a acid. So notice that you're going to end up, when you see this, you're gonna see that, oh, okay, I have 2 products, but you have to be careful because every time you see this, it's going to dissociate into water and sulfur dioxide. So instead of having 2 products, you're gonna have 3 products. So the correct will be the three products you're gonna generate is gonna be K2SO4 aqueous plus water plus your gas. Those are your your three products, not two. So this is your three products. Notice here, this is a carbonate. Be careful when you have carbonate. It's a base and an acid. Notice how you generate three products. You are going to be giving a chart. You're going to be given this chart. What I'm going to remove is this part of the chart. So make sure you know how to use the chart because you're going to be giving a gas evolution in your exam. The best question that you can practice, it's going to be this question for your exam. Notice that they're telling you that you're going to have sodium carbonate mixed with nitric acid, and it's telling you that a gas evolves. So you want to get your reactants. At this point, you should know how to do that now and predict your product. So in this case, you're going to have three products. One of them is going to be your carbon dioxide and your water. But from here, first, don't go to the three products. Just try to get the regular two products that you will get. So you think, oh, okay, here's my product one and here's my product two. And then you're gonna see this. Go to the table. This is going to further dissociate into water and carbon dioxide. It's going to decompose. And then what happens is this is your final product. But we're not done because it's asking, no, I think we're done. Yeah, it's not asking for the net ionic. Okay, so I give you plenty of practice on the exam, on the homework for this, and we can do some together. And then we have a short video to talk about other type of reactions, and then we will be done with this chapter. Okay, let's resume our chapter and finish it. We are going to start discussing other type of reactions, and this type of reactions are going to be called oxidation reduction reactions, and for sure we also call them redox reaction. This reaction, what's going to happen is that there will be a transfer of electrons. So when you see the word redox, oxidation reduction. So something is oxidized and something is reduced. Now, those terms can be a little bit confusing, so make sure that you find one way to memorize it and always follow only one way. Because it can be a little bit confusing. In this example, this atom doesn't have a charge. That means it's carrying a charge of 0. This atom doesn't have a charge, it's carrying a charge of 0. However, in this molecule, the charges are different. The charges have now changed, and now they are carrying a charge. So for example, in this compound, iron is carrying a charge of 3+. Oxygen is carrying a charge of 2-. Notice what happened in this case, that it went from 0, iron went from 0 to 3+. It got oxidized. The way I remember is if the charge goes up, it's oxidation. If the charge goes down, is reduction. Went from 0 to -2. So that's called reduction. In an oxidation reaction, or redox reaction, there will always be one atom that gets oxidized and one that gets reduced. It always happens at the same time. Notice that sometimes what you're gonna see is you're gonna have to calculate that charge. You're gonna have a little bit of math to do it, to be able to identify most oxidation reaction, not all of them, involve in oxygen. So as a reactant. Here, notice that we have sodium, which is 0 because it doesn't carry anything. Chlorine is 0. And here it went to N plus and CO minus. So sodium went from 0 to plus. It went up. Oxidation, and in this case, the way we write oxidation is by putting the 2 electrons, because there was a transfer. So since here you have 2 and 2 plus, so there was a transfer of 2 electrons. It gets put in the products. When we have reduction, there's transfer of 2 electrons. It gets put in the reactants. So just to give you the definition, notice that sometimes there's this abbreviation, LEO and GER. LEO, loss of electrons. And GER, it will be gain of electrons is reduction. So gain of electrons is reduction, loss of electron is oxidation. Loss of electrons is oxidation, gain of electrons is reduction. So in order for us to be able to distinguish that, we have to keep in mind, excuse me, for a second. Sorry about that. So we have to keep track of those electrons. In a reaction where electrons are transferred from one atom to another, it's called redox reactions. Atoms lose electrons, it's being oxidized. So if you're losing electrons, it's being oxidized. What that means is that you're gonna gain a positive charge. Atoms that gain electrons are being reduced. What that means is that you're gonna gain a negative charge. Here, sodium, the charge went up. So that means the sodium got oxidized. Chlorine, the charge went down. That means that it got its reduction. So in order for us to be able to determine what's oxidized and what's reduced, we need to make sure that we are bookkeeping the electrons, like tracking the electrons. So that means we need to assign oxidation states, meaning we need to assign the charge. We need to figure out the charge. Even though some of them are very obvious, sometimes you actually are going to have to do some math. You can't just make a general assumption because you're going to be mistaken. There are rules that we're going to follow when we are going to be doing oxidation states. For example, free elements, meaning elements by themselves, they have an oxidation state of 0. So that's why I was saying chlorine is 0. So if it's by themselves, it is 0. Monoatomic ions have an oxidation equals to the charge. For example, this is a monoatomic ion. Notice that their oxidation state is going to be equal to the charge. The sum of oxidation states of all atoms in a compound is 0. So the reason for that, this being +1 and -1, is because it has to equal 0. So +1 plus -1 equals 0. The sum of the oxidation states of all atoms in a polyatomic ion equals the charge of the ion. For example, here, nitrate, this has to equal to -1. So the way we're gonna do it is we're gonna assign this to -1. Oxygen, we have 3 oxygen and the charge of oxygen is -2 plus, and we're gonna call the charge of nitrogen X. When you solve for X, you're gonna see that charge of nitrogen is going to be 5. Group 1 metals have an oxidation number of +1 in their compounds. They always like to have +1. Group 2 metals, they like to carry a +2 charge. Last but not least, a rule, some compounds, they are going to go based on priority. So for example, in this case, fluorine, it will have a -1, hydrogen will carry a +1, oxygen will carry a -2, and so on. So this chart is really good for you to become familiar with. Here's some practice of knowing how to determine their oxidation state. So for the first one, you should have got 0. For the second one, you should have +1. Lithium and fluorine +1, -1. So if you try to do it by yourself, if you don't know how to do it, we can work on it together later on. And it gives you which rules they're going to be. Here's another definition of oxidation and reduction. Oxidation occurs when an atom's oxidation state increases. So like the charge increases. That's the way I remember it. Reduction occurs when the atom's oxidation state decreases. So notice here, negative to positive, it went up. So that's oxidation. 0 to -2, it went down. So that's reduction. Now to add to that, in an oxidation and reduction occurs at the same times, right? In a reactant that gets reduced, whatever atom that gets reduced, the other reactant is called a reducing agent. The agent always contains the element that is oxidized. So basically the opposite. For example, here we knew that sodium is being oxidized. So because sodium is being oxidized, is the reducing agent. So as long as you get the first part right, the second one is easy because it's always the opposite. Then we have chlorine being reduced. It must be the oxidizing agent, opposite. So try this on your own and I will give you the answer soon. So once you have assigned the oxidation state, you can realize that in this case, nitrogen was reduced, which means is the oxidizing agent, and sulfur is the oxidizing agent, which means is being oxidized, which means is the reducing agent. And same for the other one. So you're gonna have a question like this. I have given you some of the homework to practice, but we can do some, definitely we can do some together. The last type of reaction I need you to become familiar, it's going to be combustion reactions, which I had mentioned earlier. Combustion reactions is pretty much a hydrocarbon. So something hydrogen and carbons reacting with oxygen and generating water. So those are the most simple reactions. You want to make sure you become familiar with that. And in combustion reactions, you always are going to, if you have carbon involved, you're going to generate carbon dioxide. If you have hydrogen only, you're going to generate water. If you have sulfur, you're going to generate this gas. If in your reactants you have nitrogen, you're going to have those products. So the way you're going to be asked this question will be combustion. So notice that you have carbon and oxygen. So what that tells you is that your products, you're going to have carbon dioxide and water. Notice in here, you have your nitrogen, you have your carbon, and remember that you're reacting this with oxygen. So it's going to, this reacts with oxygen. So in this case, notice that you're going to have water, you're going to have carbon dioxide, and then you're also going to have NO2 as your products. And those are your products. So that's pretty much the last reaction I need you to know. We're going to do some practice, but this completes chapter 4.